So I had a question on the Discord about this question here, 2617 6b. Lies of an inextensible string, length 3a, attached to a point, mass m, attached to the point string, so it makes an angle theta with a vertical, so it's being held in place. String taut and cos theta is 2/3, so we know the angle we start with, which is always useful. Is then projected with speed root ag in the direction perpendicular to AB. You guys can't see my it does that. Where are we? It does. So it's here and it does that. In subsequent motion, the string remains taut. Basically, we always are working in circular motion. There's no free-falling projectile bit anywhere. If there was if the string wasn't taut, it would suddenly be a projectile at whatever angle it was moving when the string went slack. And then when AB makes angle beta to horizontal, the speed of particle is v and the tension in the string is t. Okay, so before we look at the question, I would kind of logic out or do your diagram and see what's happening. So we have our string, and the string is length 3a. We have mg down. We have tension up. The velocity is going to be ag, and the angle is theta. So that's what's happening at the start of the situation. The string is held there, then it's pushed upwards. Now, because we're in the vertical circle, it's all about conservation of energy. So that's the E equals mgh plus a half mv squared. Why has the encoder decided to crash on me? Well, I will. Hopefully the sound will keep going. The image may change a little bit, but hopefully the sound will keep going. I don't know. One of these days I can put the video and audio working at the same time. So our total energy is that. We can figure out from our starting case what the total energy of the system is at all times. So what I would do is I would draw a line down here, call that 3a. We can then draw our dotted line here. This is our height above our equilibrium position. That's our potential energy, because we have no potential energy at the bottom of the swing because the mass can't fall unless it is removed from the string. So that's our h. So the total is 3a. The side of that triangle is 3a cos theta. So I think we can say that the starting energy of the system is mg h, which is 3a minus 3a cos theta. So that's our mgh, plus half m root ag squared. And I know we know some of that stuff, but I'm just going to leave it the way it is so we can see where everything is. And then when we equate it with our second situation, we'll figure it out. So this is our starting situation. We have our height above our minimum point of our minimum potential energy, which is 3a down, which is fine. Okay, so then we go again and we can draw another one where we go beta is here. We have our mass here. I think the image is going mental, but hopefully it'll make sense. Mg down, tension that way, and we can find the height again where we have 3a being the length of the string, and so that if that's beta, that's beta. So this is 3a sine beta. So in this new scenario, or at this new part of the subsequent motion, it is the energy is mg by 3a minus 3a sine beta bracket plus a half mv squared. And that 3a minus 3a sine beta is not obvious in the marking scheme where the hell they got their numbers, or that this is what they're doing. They probably are either skipping a step or skipping it because it is completely unnecessary. Because if you know what you're doing, all we care about is the 3a cos theta and 3a sine beta. But in an exam, we're not likely to be thinking at that high level because we're panicking and we've got 2.5 hours. We want to get things done with a bare minimum of fuss. So I just do this, think about what the minimum potential energy is, so that would be the mg with 3a, and then we find the height in that way. So our h is our 3a minus 3a cos theta. So we need to equate these two things because we know the total energy is the same either way. So that would be 3mga. We know cos theta is 2/3. Yep, cos theta is 2/3. So that's minus 3a by 2/3 is 2a mg. Is that right? Yeah. Plus a half mag. And that equals to 3mga minus 3mag sine beta plus a half mv squared. Now there's m in everything, so I'm going to cancel the m's out in everything. So m. And there's a 3ga left on both sides, so that and that can go away. And then I'm going to multiply everything by 2. That will give you minus 4ag plus 1ag equals minus 6ag sine beta plus v squared. Oh, and then we have it. Okay, cool. V squared is 6, or not 6ag. Yeah, no, v squared is 6ag sine beta minus 3ag. And factorizing out everything we can, 3ag times 2 sine beta minus 1, which I think is exactly what we wanted, which I didn't tell you what it was. The first part was to show that v squared was that. Sorry, I must have lost a little bit of the question from the previous time I recorded. So that is the first part, was to show v squared equals that. Now find the minimum value and maximum value of t. So this, the string will move, does stuff. At some point, because it's moving in a vertical circle, gravity is having an effect on the tension. Because let's say we go, think about the extreme cases. If we were to think about the string very, very close to horizontal, gravity is working straight down. Tension is almost horizontal there. Supposed to say T. So the amount of gravity that is affecting the circular motion force, the mv squared over r, is always towards the center of motion. So the mv squared over r is always towards the center point of motion. So if we were to decompose the mass here, it's a very small amount of gravity is working against the tension. Whereas if we have something that's much closer to vertical, we have our whatever the tension is at this time up, we have the mv squared over r up towards that center of the circle, and gravity is down. And in this case, the amount of gravity that is working against the tension is way bigger. So the maximum T is going to be when we've got a big chunk of gravity working against it, and the minimum is when we've got a very small amount of gravity working against it. So I think the maximum is going to be when, my assumption would be the maximum is when the string is vertical, where you've got mg straight down, T up. So that would be, what is it? mv squared over r equals T minus mg. But we know what v squared is because we have an expression for it. It's that thing. So that would mean that m over 3a, because that's our r, times 3ag by 2 sine beta minus 1 equals T minus mg. We hope. But beta is 90 degrees in this case. So sine 90 is 1. You think I'd remember that. So there. We have mg by 2 minus 1 plus mg equals T max. So the T max is 2 mg. So that's how we get the maximum, when the gravity has the most effect on the string. And then where the minimum effect on the string would be when the string goes horizontal. However, what if the string doesn't go horizontal? So if the string goes up and just keeps going, we can go past horizontal or go up to horizontal. Either way, we have to be really careful, because actually possibly if it goes up above the horizontal, then the tension gets even less. So, yes. So we need to see, is there a point at which the velocity goes to 0 and that it stops moving? Because that's where it gets to its highest, which is where it has the minimum tension, I think. So let's see. So v equals 0. So that would be v squared is 0 equals, or again, 3ag 2 sine beta minus 1. So that would be, we'll divide out by ag. Then you bring divide out by 3 as well. Well done, Neil. Then that would be half equals sine beta. So beta equals 30 degrees. So all you have to do then, we draw our little situation so we know what's happening. We have our mg down, we have our tension up. We know that's 30 degrees, that's 30 degrees. And we know our mv squared over r. So decompose your gravity to see how much of it is going into working against our tension. So that's 30 there. So it'll be mg sine 30 against tension. So our mv squared over r over 3a, that's our r, is t minus mg sine 30. But we know v has gone down to 0. So that whole thing there is 0. So that would be t equals mg sine 30. And sine 30 is a half. So that means t equals mg over 2, which is thankfully less than what we said was the maximum. So I'm pretty sure that I can be confident that I got those two answers correct. Now there is another way to look at it, very quickly. If you were to do your diagram, we don't know what that is. We have gravity down, mg, break that down into, I'll be super quick now, so mg sine beta, mg cos beta, tension's that way, and mv squared over r is that way. So at any moment, mv squared over r equals t minus mg sine beta. But we know what mv squared, we know what v squared is, it's that 3ag thing. So we have m by 3ag 2 sine beta minus 1 over 3a equals t minus mg sine beta. I'm scrolling this down, but I think you can follow along if you're this far with me. So that would be 2mg sine beta. Why has that decided to do straight lines? 2mg sine beta minus mg equals mg sine beta, or no, plus mg sine beta equals t. So that is 3mg sine beta minus mg equals t. And what you can do there, if you wanted to, you can differentiate that with respect to beta, find a turning point, and you'll get a maximum and a minimum in that way. Or you can just, again, logic it out and see what you get. So you can use calculus from there if you wish. And, challenge yourself, see if you can figure that out, because it is possible you'll have loads of time at the end of an exam, or you'll have some time, and you can find it that way. So there's lots of different options, but I think key with this one is because it's in circular motion, or because the string remains taut, we always have circular motion in effect. We always have a tension and force. Therefore, we, instead of decomposing everything to be with the gravity, you break it down to be in the reference frame of the string itself and the force. But I hope that answers your question. If not, just give us a shout and we'll figure out what's going on.